各位同学早安。那因为在上课前，我们还是说明一下，就是关于第一次线上小考上传档案，这件事情啊，因为有的同学有反映说，就是第一次，所以上传的时候操作的这个程序不是很熟悉，所以我们统一就是在第一次这次小考，我们可以那个接受，就是后来再补交上传这个小考解答的这个过程。哦，那这次的考试我们有发现，有的同学在呃拍到上传的这个动作，其实照片那个解析度不是很好，那这个可能希望同学在下一次要做个改善哦，看能不能上传这个比较解析度比较好的这个解答过程，那助教在进行这个批改的时候会比较方便一点。那第二个，有的同学在上传的时候，并不是上传解答的过程哦，那这个可能也要注意一下自己上传的图片档案是不是真的是自己的这个解答过程。所以我们在第二次，也就是下个礼拜一的小考，那我们就是如果同学还是有迟交的状况，我们就不会再受理。所以希望各位同学可能要多加注意。那这次的考试成绩其实大部分人都还是考得蛮好的，那有30几个人都还是介于90到100分。哦，那我希望就是各位同学在防疫的期间，其实还是要注意自己的身体健康。那关于小考这部分，也希望大家可以准时收看这个线上的录制课程。哦，那我一样还是会在每次上课的礼拜五去提示大家下一次的这个小考可能必须注意的范围以及考试的内容。OK, okay, so we go back to look this exercise. So again, this exercise still focus on the Bernoulli equations and the continuity equations, but our target is focus on the venturi. Okay, so this is a venturi, and we know that the water with a density of the 1,000 kilograms per meter cubic, and the water flow pass through a vertical venturi meters as shown here, and we know that the pressure gauge is connected across two taps. So we have the tab 1 and the tab 2, and the question tells us the area ratios between the tab 1 and tab 2 is 0.5. So there is the pipe, and the area is dot. So we know that the A2 divided A1, the cross-section area ratios is equal to 0.5. And we also know that the V1 velocity in here is the 10 meter per second. Okay, and please find the pressure difference recorded by the pressure gauge. So we know that here is the patch isometric pressures 1 and the pressure isometric pressure 2. And what is the delta P in here? And for this problem, we assume the flow is uniform flow, and that viscous effects are not important. Okay, so first, if we follow the continuity equations, what we already know in these problems. And this is the problems is the uniform flow. So actually we know for a uniform flow in the ventaries, Q1 will be equal to Q2. So the V1 A1 is equal to the V2 A2. Okay, so we actually know that the V1. So what is the V2? The V2 is equal to the V1 multiply the A1 divided A2. Okay, so the V1 is the 10 meters per second, and the A1, A2 is the ratio here. So we know that this is 0.5 over 1, and the answer of the V2 velocity flow is 20 meters per second. Okay, and the second part, we know that the Bernoulli equations. So we have the Bernoulli equations. So we can write down the balance between the pressures and the velocity items for Bernoulli equations. So we know the piezometric pressure for 1 plus the 2 over rho V1 square is equal to the pressure, piezometric pressure 2 plus 2 over rho V2 square. And then we know that the pressure difference is the piezometric 1 pressure minus piezometric pressure 2 is the delta P, and then is equal to 2 over rho the V2 square minus V1 square. Okay, and we know that is the 2 over rho. The rho density is 1000. Okay, and the V2 is 20. So there is the 20 square minus the V1 is the 10 meter per second. Okay, so the delta P is equal to 1000 divided 2 is 500, and multiply the 20 square. So there's 400 minus the 100, and this is the 500 multiplied 300, so it's equal to 15,000,000. And we know that it finally is 1050 kilopar is our answers. So the idea for this exercise is quite simple. We know that the phenomena highlight this exercise is when we have the small cross-section area and will result the high flow velocities. The high flow velocity is based on the Bernoulli equations. We know that there is also the lower pressure area. So small cross-section area, and it will have the high flow speed. The high flow speed will result the low pressure region. Okay, so based on these ideas, we wondering to know the cavitation problems. So as you can see the solid line here, this is the phase line. So what kind of the phase we have along this line? This is the line for the liquid to vaporous phase. So if you can take a look, if you look, the conditions of environment temperature is 15 degree, and then you will have the vapor pressure around the 1.7 kPa. So that means if you under the 15 degree environment temperatures, the vapor pressure is the 1.7 kPa. If your environment pressure is lower than the vapor pressure at these certain temperatures, and your liquid will convert to the vapors. Okay, so the difference you see when the temperature increase and the vapor pressure also increase. So the higher environment temperature will have the higher vapor pressure. Okay, so what's the problems if your environment pressures under the vapor pressures? As we know, we call that is the cavitations. And the sentence right down here just tell you your environment pressures lower than vapor pressures at a certain 50 degree environment temperatures. And then you will have vapor bubbles, and the vapor bubbles will result the instantaneous pressures to be a very higher pressures around the 800 million parts. So the vapor bubbles is very terrible because its pressures is quite higher. Okay, this is very terrible phenomena caused by the cavitation phenomena. So the two figures shown here, the infrastructures like the fan and the spillways will be destroyed by the cavitation problems. As you see, there are some holes caused by the vapor bubbles. But the cavitation is not always the trouble. There are some advantages for the cavitation. The one shown here is the supercavitating operators have been developed in which a large bubble envelopes the torpedo, significantly reducing the contact area with the waters and leading to significantly faster speeds. And the second is the cavitation can be applied for destruction of the kidney stone. Okay, so I just list two advantage for cavitations. So what we need for engineering problems, we would like to predict the cavitations. And there are some locations with the low pressures. As we know, if we move to the high elevations points, and then we will have the lower pressure. And if your locations are with the high velocity speed, based on the Bernoulli equation tell you the velocity increase and result the pressure decrease. And also the suction side of the bounce also result the lower pressure. Okay, so this is a cartoon figure showing here is for the venturi. So we know that the venturi, along the venturi different cross-section areas, you will have a different speed. So in that way, you can see that this is the A1 and the A2, and then maybe this is the A3, and this is the A4. So different cross sections will have a different area, and we know that this is a large, and this is a small. So based on the continuity equation, you know that the A1 V1 velocities is equal to the A2 V2, right? So this, if you have a large area, and you will have the small velocity. If you have the small area, you will have the large velocity. So the small area is here, and the velocity will increase. And as I emphasize that the velocity increase, and based on the Bernoulli equation will tell you the pressure need to decrease. Okay, if your environment pressures decrease to touch the vapor pressures under a certain temperature, and your liquid will convert to the gas, and the gas will have the vapor bubbles, which we don't like because the vapor bubbles will induce very large pressures to destroy your structures. So for this problem, when we design the ventures, and we will control the flow velocities across these small section areas, because if the velocity is too high, the pressures will lower than vapor pressures to result the vapor bubble. Okay, so the velocities is limit for engineering problems. So this is the one exercise, and the exercise tells us we have the beer particle, okay, and at the depth where the absolute pressure is the 18 psia. So have the point 1 here, and then the pressure at the point 1 is the 18 psia, and the flow to the right hand side to touch the particles, and we know that in here is a stagnation point, and the maximum velocity will be on a sphere across 90 degrees. So that means the string line will along the particle surface until here. We call that is point 2, and the velocity at the point 2 is the V maxima. Call that is V2, and the velocity at the point 1 is V1. And the exercise tell you the V2 in here is the 1.5 times V1. And the problem in here for the density is the 2.4 pound mass divided the every cubic. Okay, so please calculate the speed of the spheres at which cavitation will occur. And we know that based under these temperatures, the vapor pressures is equal to 0.178 psia. So calculate the speed. Okay, so that means what is the V1? Okay, so we just first we need to know what is the pressure unit, the PSI. The PSI means the pound force divided the inch square. So if you would like to convert the PSI into the PSF, so what is the PSF? The PSF is the pound force divided the Ft square. And because we know that the 1 Ft is equal to 12 inch. So in here, we need to multiply the 12 square, and then we can convert to the PSF. So for our questions, we know that the P1 is the 18 psia, and if we convert to the PSFA, we need to multiply 18 by the 12 square, so we have the PSFA, and this is equal to, so use your calculator, it's 1/8 multiplied 12 multiplied 12. So the pressure for the P1 is 2592 psia. And what is the P2? The P2 is the pressures at the location on the top of the sphere. So because our questions is focused on that the cavitation phenomena will occur. So that means the pressures at this point should be equal to the vapor pressures. And the vapor pressure at the certain environment temperature here is 0.178 PSIA. And so in this, we need to multiply the 0.178 with the 12 square, and use your calculator to compute these values. 0.178 multiply 12 multiply 12. So the answer in here is 25.3632 PSFA. So based on the Bernoulli equations, and the Bernoulli equation tells us the pressure 1 plus the gamma Z1. Z1 is the elevations for the location 1, and the plus the 2 over rho B1 square is equal to the P2 plus the gamma D2. D2 is the elevation on the top of the spheres, and the plus 2 over rho B2 square. And as same as the previous exercise, we ignore the elevation difference between the Z1 and the Z2 because the sphere particle is quite smaller. Okay, so we don't have the items for the Z1 and the Z2. So we actually know that the pressure difference P1 plus minus the P2 is equal to the 2 over rho V2 square minus the V1 square. Okay, and we also know that there's the 2 over rho, but the inside velocity, the V1, V2 is equal to the 1.5 square minus the V1 square. So there is a 1 square, and we take the V1 outside. So this is the V1 square. Okay. Based on the V2 is equal to the 1.5 times V1, so we can rewrite the equations to the 1.5 squared minus 1 squared. Okay, we just put the number into the equations. So the P1 in here, we have the 2592 minus the 25.632, and the unit is the PSF. So there is the unit is the bond force divided the Ft squared is equal to the 2 over rho. So we have a 0.5 multiplied the rho is the 62.4, and the unit is the bond mass divided the Ft cubic, and there is the 1.5 square. So 1.5 multiplied 1.5 minus 1 is equal to 1.2 25, and the outside is the V1 square. The unit is the Ft square divided the secant square. So if you take a look, the unit is not equal because there is the bond force, but there is the bond mass. So we need to convert the bond force to the bond mass related. So follow, we know that the one bond force is equal to the 32.17 bond mass multiply the Ft divided the secant square. Okay, so we change that. We just compute the answers for the pressure difference is 2592 minus 25.632. So the pressure difference in here is 2566.368 multiply the 32 1.17 to convert the bond force to the bond mass multiply the Ft divided the secant square and also divided Ft square over 1 is equal to, there we just take the number is 0.5 multiply 62.4 and also multiply 1.25. So numbers on the right hand side it is equal to 39 and the unit 39 V1 square. And the unit is the bond mass Ft cubic multiply the Ft square divided the secant square. So if you take a look, the unit balance on the right hand side and left hand side now is equal each others. Okay, so we just reorganize. Finally, we know that the V1 square will equal to the 2566.368 multiply the 32.17 and divided the 39. So the V1 square finally is equal to the 2116.92, and then we take a root, and finally we know that the V1 is equal to the 46 Ft per second. Okay, so this problem is very important, and this is the problem related to the predict the cavitation problems. So if for your questions at some point the velocity will increase, and then you need to take care about that the velocity increase cannot too high. If the velocity increase is really high, and in that the point will have the lower pressures. If the pressures down to vapor pressure, we will have the cavitation. So we need to avoid this cavitation phenomena, we try to control the velocity in here. So you will have a certain velocity in here. The v is need to less than 46 ft per second to avoid the cavitation problems. Okay, so this is the final exercise related to the cavitations problem. And the cavitation problem, we only need to apply two equations. One is the continuity equations. Another is the Bernoulli equations. So combine two equations, you can try to answer some problems like the cavitations, and or try to understand the velocity changes at the different cross-section area. Okay, so for the next, we focus on the different is the differential form for the continuity equation. But before that, in next semesters, we have the Venturi experiment for our fluid mechanism, adaptatory experiment class. Okay, so this is our instrument, and if you take a look, the one Venturi in here, so we have a Venturi bubbles in here, and again, because this is a Venturi, so the cross-section area will change along the Venturi. So we exactly know that we have the A1, and maybe there is the A2, and there is the A3. So based on the continuity equations, we know that A1, B1 will equal to A2, B2 equal to A3, B3. So at the different cross-section area, we will observe the different velocity field. Okay, and we know that the area larger will have a lower flow velocity. And also we know that the Bernoulli equation tells us we have the P1 piezometric pressure P1 plus the 2 overall P1 square will equal to the piezometric pressure P2 plus 2 over 1 rho P2 square. So we also know that based on the Bernoulli equation tells us the higher velocity will have the lower pressures. Okay, so if we have the continuity equations and then we have the Bernoulli equation, we can predict the velocities or predict the pressures at the different cross-section area. Okay, so if you take a look, there are some bubbles connect to the pipe connect to the Venturi tube. So we exactly know the rising height at the different bubbles, and the rising height can tell us the pressure informations. So this kind of the pressure is directly from the pressure pipe. So we know that the true pressures, but based on the continuity equation and the Bernoulli equation, we can predict theoretical pressures. So we just compare the theoretical values and observed values. There will have some difference. So how about difference? The difference is caused by we call that the heteros. The heteros is contribute from in real case, we will have some viscous effect. In our class, we always assume the condition is under the viscosity effect are not important. But in real case, we will have the viscous effect, and this is related to the Bernoulli Equations. So that's why based on the theoretical, we can compute the velocity or pressures, but they will have some difference compared to the absolute measurements. And the difference we call that is the heteros caused by the viscous effect. So the next semesters, you will have these laboratory experiments, conduct these experiments to understand what's the difference between the theoretical values and the observed values. And just based on the continuity equations and the Bernoulli equations. And the heteros, we will teach you how to compute the heteros in the following class. Okay, so right now for this chapter, the final items is some important formulas. So the first one is a differential form of the continuity equations. Okay, so maybe we have the 10 minutes breaks, and after the breaks, and we go back to continue our we will derive some equations. The first one is a differential form of the continuity equations. And the following, we will introduce what is the string functions and the potential functions for the three-dimensional flow. Okay, so let's start to 10 minutes break. Okay.